Furniture typically consists of elongated and planar parts that are connected together by glue, nails, hinges, screws, or other means that discourage disassembly and reassembly. An alternative approach is to use an interlocking mechanism where the furniture components tightly lock with one another by a carefully planned network of joints. Such a structure can only be disassembled in a certain order, starting from a specific key, which is the only mobile part in the assembly. Interlocking furniture has several advantages. First, it facilitates easy assembly, disassembly, and reassembly. Second, the global interlocking scheme restricts the assembly and disassembly order, thus tightly locking the components together. Third, external fixtures such as hinges are not required. This allows the intended aesthetics of the design to be kept. The challenge in designing a network of joints is that local analysis is not sufficient to guarantee a global interlocking structure. When planning the joints, we need to globally analyze the whole design. However, since there's a huge space of joint combinations, it requires an enormous amount of exploration effort. Second, for a valid joint combination, all subsets of parts should be immobilized except the key. This means we need to explore a huge number of subsets that increases exponentially with the number of parts in the model. To design an interlocking furniture assembly, we represent a furniture model by a parts graph and identify cycles in the graph. Then, starting from the key part, we try to make an interlocking group around it by examining the surrounding cycles. To make this group interlocking, each part first receives a 6-bit code which indicates the part's mobility in major axial directions. By carefully planning the joints to restrict the part's movement, we can immobilize every part in the group except the key. Now let's go back to the parts graph. After the first interlocking group, we iteratively create more interlocking groups and lock adjacent groups with order dependency. By this scheme, the whole assembly becomes globally interlocking, as shown by a mathematical proof in the paper. We demonstrate the effectiveness of our approach on several globally interlocking furniture assemblies of various shapes and complexity. (3D fabrication). Here we show the 3D printed parts of a console table. By following the assembly order, we can put the parts together and construct an interlocking assembly. Here we show the assembly process of a multifunction table and a chair. And here are all the assembled results. They are all globally interlocking by a specific key part.